So, Maru,
How much is the network a factor in delaying the process of parallel computing?
Well, it depends very much on the program that you're doing, and what happens in practice is if it's not good enough, you find another machine. But part of the art of developing algorithms for this is to find a way to partition the problem in such a way that there's as little communication as possible. So, for example, in the case of the particle simulation that we showed that plasma instability, it was partitioned in space. Each processor was responsible for a quarter of the volume, and particles would sit inside one volume, and when they crossed the boundary, they would be, through the network, would physically be passed to that machine. But again, it was only particles at the surface of the volumes that would actually be sent. The ones that are inside don't get sent. So you try to keep that traffic to a minimum. But it's in some sense an art how to find a way to break up your problem that has as little communication as possible.
And what happens when one of the Macs dies? Does it continue? The three takes over, or at this point?
Currently, with our library, what we've done is there's timers so that if I haven't heard from you in 5 minutes, I will assume that you're dead and will do something. Typically, I die. I shut down. Now, in principle, it's possible because you're detecting that error. You might be able to save your state. I mean, you could save your state to do that, but in practice, it's not that useful because you've lost the data for the one that was over there. So unless you can somehow regenerate that, it's not even that useful.
So you have to more or less start over in your...
Well, no. What we do is we save restart files. So if we're doing a long run, maybe every hour you will dump out the disk your current state, so that you'd go back to the last saved state. So you'd hopefully never lose more than an hour. People do this dumping these restart files more often than that. But we have to code that in ourselves. So in our case, we'll dump all the particle coordinates to the disk because we can recover from that and continue the trajectories.
One last question. Could parallel computing, for example, help in these real-time kind of simulation applications?
Switch me on. Okay. It depends on what kind of visualization you're talking about.
Like your last presentation.
Like these. The problem is that, well, okay. I guess it's similar to other issues in parallel computing in terms of how much computation do you have for how much communication time, how much data you need to transfer across the networks here. Typically for something, let's take an example like Atom-in-a-Box. What I tried to do specifically is to optimize with every technique I could possibly think of to get this as fast as possible. So the computation time was really small. The amount of data that we're talking about, these are each pane that's here is about 256K of 32-bit images. So we're talking about a half megabyte, and if we want to convey a half megabyte in the 20th of a second, as the rate we're going here, that's what 10 megabytes per second, and that's the very, very limit of 100 base T. So the idea of getting this data across that fast, it's just, in this case, it'd be for Atom-in-a-Box. It probably wouldn't be
practical. That's where the network is your bottleneck.
Yeah, that's where the network is the bottleneck. This is an example of that.
There's not enough work to do in this case. But if you had a problem that had more work, and a good example might be, if it takes you 30 seconds, a minute, 10 minutes to generate an image, then that would be ideal for this kind of system to do that. So you kind of have to pick your thing. However, it's a changing target because gigabit network is probably going to be around soon, and that will, in principle, an order of magnitude, but probably in practice, maybe 30–40% improvement. So that changes the ratio as well. On the other hand, processors are getting faster too. So.
And I noticed you put FireWire on the same line as network. Are you exploring doing your parallel computing over FireWire?
Well, we actually did. There was a company recently that sold a product, or are trying to sell a product, which is TCP/IP over FireWire. And so they had a demo version. We downloaded it and tried it. In principle, it's very attractive because FireWire is 4 times faster than fast Ethernet. So it looks like it'll be very interesting. However, when we tried it, it basically gave errors. And so we were not able to, it wasn't reliable enough at this point. However, we're in contact with the company, and we have given them our code for them to debug it and hopefully get it right. I think FireWire has some interesting features and some less interesting features. One very interesting feature is that in our header file is the destination and RAM where that thing could go. So, so it's possible to have very, very lightweight, very low overhead trafficking. On the other hand, it's a shared bus, so it would be difficult to scale to very large systems. But on the other hand, we don't have very large systems, so it may be good enough for what we want to do, or maybe some combination of FireWire and some other kind of technology to cascade one or the other. It looks interesting. I think for small systems, if they get it right, it probably would be interesting. But gigabit's going to be very competitive, and it may. It's hard to know at this point how it would pan out. But FireWire is also planning to speed up. So I think they plan to go to 800 megabits before long as well. So currently, we're using it primarily for disk. There's some really neat disks that we use as our primary archival medium for.
Yes, we have another question.
Most people around this area of campus utilize parallel computing for render farms.
Yeah.
Where do you see everything that you've shown us here today taking that, characteristic of parallel computing?
Yeah, I mean, you could do that. In fact,
I mean, is it happening now? I guess I'm not aware, because I know there are some higher-end 3D applications out and
I mean, currently,
expecting
I don't
to come
think
out.
currently people are running parallel Macs as render farms. But I don't see any reason why it wouldn't be the case. In fact, probably largely the same software. I mean, if these render farms were written using MPI standards, which would be the intelligent thing to do, rather than some low-level driver, the same stuff would run here. So it won't really matter. But I'd have to, you'd have to see how much. Well, I mean, mostly these things are Unix-based. So what kind of Unix systems did they put in there, or did they stick to the standards? On the other hand, Mac OS X will, in fact, be Unix-based also. So at that point, you could probably, even if it was Unix-based, you could just port it over as well. So I don't know really what's going to happen. I think this AltaVec is very interesting. In fact, it's a multimedia chip. That's what it's for, this vector processor. So someone could exploit that and get some, as you saw, some really amazing speed-ups as well.
But in principle, there shouldn't be any technical difficulties, though, right?
Right. So I think it's just as far as I know, just people haven't done it, but I don't see why they couldn't do it.
So has this kind of Macintosh clusters been adopted by any other research institution?
Yes. Yeah, we have. We were in contact with a number of people who have them. There's one cluster, I guess, in Maryland and another in Wisconsin. Some of these are being used for medical imaging. These are people with real-time constraints to invert some image because the guy's sitting there, So you want to do it as fast as possible. And so I know those are successful. I had one email from someone who basically they get pretty much they have four Macs and they got essentially 4 times speed up, even with our slow library. There's actually another Mac cluster here at UCLA in the statistics department. They have 16 G4s, and it's primarily going to be, I believe, intended for education. They want to teach people how to do parallel
There's
programming.
also one in Canada, remember?
Yeah, the first one that cloned us was at the physics department in York University in Canada, and so they built one very early on. And we get email virtually almost every week from somebody who's found the stuff on our website.
Columbia's worked on it, so
a lot of these are just
Columbia, yeah.
students who just want to learn what is it all about. I mean, how does this thing work? And they're not necessarily professional researchers, but they just want to learn. And the Macs are sitting there,
Right.
they're wired together. It works. So
Have you calculated like where it might be like the ceiling limit of the cluster, or if there is
You know
one?
how many?
Yeah.
Again, I think it's very, very problem dependent. We've done this fractal demo with 16 max, and we've gotten
14
gigaflops out of a peak speed of 16. So
The statistics are
Is
perfect.
it? I mean, is it? When does it?
well, eventually, what you
you're
see
adding-
on the screen is you get you saw how it split the
Right,
screen.
right.
Eventually, the layers are this tiny, and so now the communication starts to become a significant part of that. For that fractal demo, it looked like 16 was probably a good number. Probably you could still get maybe good speedouts with 32, but beyond that, probably wouldn't do it. The worst one is fast Fourier transforms. When we run FFTs in parallel, those are kind of the worst thing because everybody has to communicate to everybody. And we found that we scale to about 8 nodes on the FFT. But FFT is historically known to be kind of like the worst benchmark in general, although you can certainly design something slower.
And parallel computing versus multiprocessor in a system?
They're basically orthogonal, and we could run basically whatever's on one node. We could further split that into two. The two pieces don't have to know about each other, so the MPI part and the multiprocessing part could be done completely independently, and I don't think that would be. In fact, the current state of the art of massively parallel computing is essentially that. They're distributed SMPs, where you've got 4, 8 nodes, CPUs on one node, and then there's message passing across the nodes, and there's shared memory programming. But basically, we have, each CPU now has its, push subroutine or whatever. You bifurcate that on each node. So the two. But that's something internal to the node. The message passing knows nothing about how each node internally decides to further break up the problem.
Okay, so I would like to thank you for this wonderfully inspiring presentation, which I think and I hope could also have some applications on the fields of design. I believe so. And so thank you very much. And this concludes the final lecture here of the quarter here at the EDA space. Okay, thank you.
Thank you.